Scaling is the solution. That is the premise the entire cloud infrastructure model rests on. When demand rises, add more capacity, and the system handles it. So when an engineering team watches their application slow to a halt while simultaneously watching their server count climb from 20 instances to 200, something feels deeply wrong. Not just frustrating, wrong in a way that contradicts the whole reason the infrastructure exists. They scaled. Response times got worse. The scaling itself broke the system. This is not a rare edge case. It is a category of failure with a specific name, a specific mechanism, and a deeply counterintuitive character, because it does not come from doing something wrong. It comes from doing exactly what you were supposed to do, at a speed and scale the surrounding system was not built to absorb. Consider what happens when a city's water supply is cut off. A main pipe fails at 7 in the morning. For 4 hours, no water flows to an entire neighborhood. Residents adjust. They stop cooking. They stop running taps. They wait. At 11, engineers restore the supply. Within seconds, every household in the neighborhood turns on a tap simultaneously. The pipes, which were designed to handle the gradual, staggered demand of a normal morning, are suddenly asked to deliver maximum flow to every address at the same instant. The pressure drop is catastrophic. Some houses get a trickle, others get nothing. The restored supply, designed and sized for normal distributed demand, is overwhelmed by demand that was never normally distributed because everyone was waiting for the same signal, and the signal arrived for all of them at the same moment. This is the core structure of the problem that scaling creates. Not a steady flow of demand arriving at a system that grows to meet it. A synchronized surge of demand, all hitting at the same instant because all parts of the system were idle at the same instant, arriving at components that were never designed to absorb synchronized load. The thundering herd is what this pattern is called in distributed systems, and it appears in scaling failures in a very specific form. A large application normally distributes its traffic across many running servers. Those servers hold data in memory, cached results of expensive database queries, session information, frequently accessed records, so that common requests can be answered quickly without going back to the database every time. The cache is warm. It has been serving traffic long enough that the most frequent queries are already sitting in fast memory, ready to be returned in milliseconds. Now a sustained traffic spike arrives. The auto-scaling policy fires, and the system adds 100 new servers to the pool. Those servers begin receiving traffic immediately. Each one has an empty cache. Every request that arrives at a new server asks for something the cache does not have. The server goes to the database to fetch it. 100 new servers, all with empty caches, all routing their first requests to the same database simultaneously. The database, which was handling traffic load from the existing fleet without difficulty, is now absorbing a surge of requests from 100 new sources all at once, each one asking for data that no cache is yet holding. The database saturates. Query times stretch from milliseconds to seconds. The existing servers, which were handling traffic, now find their database queries slowing too, because the database is occupied with the avalanche from the new fleet. Response times across the entire application climb. Users who were being served adequately before the scale-out started hitting timeouts. The auto-scaling added capacity that made performance worse, because the act of adding it created a synchronized demand spike on the component it depended on. The pattern deepens when you add client behavior into the picture. When a user's request times out, most applications retry it. The client tries again, after a short wait, or sometimes immediately. When response times are degraded across an entire application, not one user is retrying. Thousands of them are, all at the same time, all generating new requests into a system that is already overloaded. This is a retry storm, and it is self-amplifying in the worst possible way. The system slows down. Clients retry. The retry load makes the system slower. More timeouts, more retries. The load the system is absorbing grows not because demand grew, but because the system's own degradation is generating second and third attempts for every original request. There is a cruelly elegant irony here. The more reliable and persistent the client, the more diligently it retries on failure, the more aggressively it amplifies the load during an incident. A well-intentioned retry policy becomes an accelerant, the water tower neighborhood again. Not only did everyone turn on their tap at 11, but everyone who got a trickle turned it off, waited 10 seconds, and turned it on again. None of these failures require anything to go wrong in the traditional sense. The auto-scaling policy executed correctly. The new servers provisioned successfully. The clients retried as they were designed to. Each component behaved exactly as specified. The failure came from the interaction between correct behaviors at a scale and synchronization that the system was not designed to handle. This matters because it points toward where the fixes have to live, not in correcting mistakes, but in deliberately introducing imperfection into a system that was too synchronized. The first approach is jitter. When new servers start up and their caches are empty, they do not all reach for the database in the same millisecond. A small, random delay, a few hundred milliseconds, different for each instance, is introduced before each server begins making cache miss requests. The requests that would have arrived simultaneously are now spread across a short window. The database sees a surge, but a staggered one it can absorb, rather than a perfectly synchronized wall it cannot. Jitter does not reduce the total load. It distributes it in time, which is the only distribution the database can use. The same principle applies to retry behavior, a retry policy that waits a fixed interval between attempts, every client waiting exactly 5 seconds before trying again, synchronizes retries just as effectively as simultaneous arrival. Exponential backoff with jitter addresses this. Each retry waits longer than the last, and the wait time has a random component. So clients that experience the same initial failure now retry at different moments. The retry storm never forms, because the retries never arrive at the same instant. The second approach is gradual cache warm-up. Rather than immediately routing full production traffic to new servers the moment they finish provisioning, a technique called connection draining in reverse, sometimes called slow start or traffic ramping, introduces new servers to traffic incrementally. A new server might begin by receiving 5% of the traffic it will eventually handle, rising over several minutes to its full share. In that time, its cache fills from a manageable trickle of requests rather than from a full volume surge. By the time it is absorbing its full allocation of traffic, it is warm. The thundering herd never forms because the new servers never all hit the database simultaneously at full volume. The third approach is circuit breakers. A circuit breaker is a component that sits between your application servers and a downstream dependency, a database, a third-party API, a shared service. It monitors response times and error rates on that dependency. When they exceed a threshold, it opens. Requests stop being sent to the struggling component and instead receive an immediate controlled failure response. This sounds like making things worse, returning errors deliberately, but it prevents the retry amplification loop. Clients that get an immediate error can apply back-off logic. Clients that get a 30-second timeout generate a retry storm. The circuit breaker trades a degraded experience for a stable one and prevents the retry load from turning a struggling component into a fully collapsed one. What you understand now is that scaling failure is not always a failure of the scaling system. It is sometimes the scaling system working exactly as designed, in an environment that was not built to absorb what that design produces. The thundering herd, the cold start cascade, the retry storm, all are emergent properties of correct components interacting at a speed and synchronization that creates dynamics no individual component was responsible for anticipating. Designing around these failures means accepting a counterintuitive principle. Sometimes the fix is to deliberately slow down, to add randomness, to return controlled errors, to ramp where you could surge. The instinct in a crisis is to do more, faster. The systems that survive are often the ones that knew when to do less, more carefully.